we go. Is that consistent with what we did in the example? Okay, 5 is a prime factor of 125, so we find that one single prime factor. Step 2, maybe optionally we want to print f to the screen, because after all, the program is supposed to find all prime factors of a given number. If it doesn't do anything with the factor, that means the program is not very useful. What is the last thing we want to do in per iteration? How did we go from 125 to 25, and then from 25 to 5, and then from 5 to 1? What did we do? Divide by 5. In terms of the variable names that we have introduced here, how do we express that? No, we don't. We say we update n so that n becomes n divided by f. Okay, so that way, when we find that 5 is a prime factor of 125, after printing out 5 as a factor, then we divide 125 by 5, we get 25. So 25 becomes the end of the next iteration. Then we find that 5 is a prime factor of 25. We divide 25 by 5, so we have only 5 left. But that 5 became the end of the last iteration. And then we find that 5 is a prime number itself. 5 divided by 5 is 1. And that 1 became the end. But that's the last iteration, because when n equals 1, we get out of the loop. Okay. So this is, step by step, how do we derive an algorithm? Are there any questions about this algorithm so far, or how I go from one step to the next? One thing that is important is when I'm trying to come up with an algorithm, when I'm designing an algorithm, I don't just go from, first line is loop, second line is to find a prime factor f of n, and so on. I start with the overall control structure. Identify that this is some kind of a loop. And when I identify this is some kind of a loop, I always identify when do I get out. Okay? So once you know it is a loop, you always try to identify the condition, to stay in the loop or to get out of the loop. I'm almost done here. In revision 4, I have to decide, should I go for a pre-checking loop or should I go for a post-checking loop? Either way, it's fine. You can actually, it depends on the assumption. If someone can give you an n that is 1 or less than 2, then you have to use a pre-checking loop, because otherwise, it will break the algorithm. If you're guaranteed that n is at least 2, then you can actually use a post-checking loop as well. So in this case, I would say it's a 50-50. It's an even. It's even. Basically, you can choose either one. In my notes, I use a post-checking loop, so it becomes repeat. Find a prime factor f of n. Print the value of f, and gets n divided by f. And loop. Oops. Since it's a repeat, I have to use until n equals 1. That's it. In 4 revisions, I came up with the actual algorithm. Yep.
Are you gonna define what find a prime factor of f of n is, or what to do that?
That's a very good question, because that is not one of the statement types that we have seen, before. In other words, up to this point, we have introduced assignment statements. We have post-checking loops. The print seems to be okay. Most programming languages have a way for you to print the result to the screen or to the output. But we don't have, a statement type called find a prime factor f of n. But that's the whole idea of top-down design. I only want to state what needs to be done without stating how it is done. Okay, so that's a very good question, because it brings us all the way back to the whole point of this algorithm, which is to illustrate top-down design. Okay, very good. You can also basically say, top-down design is a good byproduct of being lazy, because I was hoping that somebody already knows how to find the prime factor f of n, and I can just call that particular subroutine or use a particular operator. That was my hope, okay, as a lazy programmer. But that particular byproduct makes the algorithm better because instead of spending all the time to figure out all the itty-bitty details to find a prime factor f of n, my overall algorithm now only has 5 lines, which makes it fairly easy to understand and analyze. Is that making any sense so far? Now, is this algorithm traceable? Can I trace it? Yeah. Sure, we can trace it. Okay, but what about this line here that does not really show us how to get something done? Well, do we know how to find prime factors f of n, find a single prime factor, given a number? Yeah, we can do it not very quickly, but we can do it. So we can actually trace this algorithm even as it is. So later on, when I tried to finish the entire program, I found out that my assumption was wrong. In other words, nobody has written a subroutine or the algorithm to find a single prime factor f given the number n. So now it is time for me to say, okay, I guess I have to do it also to find out how to find a prime factor f of n. But that becomes a separate problem now. The top level problem is now solved. I have a sub-problem to solve at this point. In other words, this is a divide and conquer type of approach. I break a big problem into smaller problems, but each smaller problem is smaller. Okay? It does not have the same scope as the original bigger problem. Are there any questions so far? No questions? Okay, so let's focus on how do we find a prime factor f of n. Once again, we have to try several things so that we can get a systematic way of doing things. Now, once again, 6 would not be a very good number as an example because guess what? You guys already know all the rules of thumb to find that, 2 is a prime factor of 6. That's easy. That's way too easy. So what we need is a number that is quite a bit bigger. Let's say something like that. Okay? That's a relatively big number. It's not huge, but it's big. It's big enough that we cannot tell right away what is a prime factor of this number. So what do?
Check all the prime numbers.
Okay. Very good. Now, is it wrong for me to try to divide this number by 2?
Yeah. Yes.
It is wrong? Or is it just inefficient? It's just not very smart.
There's a better number to choose.
Now, how can you tell that this number is not divisible by 2?
It's odd.
Because it is odd. But how do you know it is odd? Because it ends with a 1, right? But that only works when you're using a particular type of base. Okay, we're using base 10, and therefore it works. Yep.
Use the modular function.
You can use the modulus function. Yes, but the modulus function is still a division. It's still a division. We're only paying attention to the remainder. So we still, we carry out this calculation. I don't really care about the quotient in this case, but I know the remainder is 1. The remainder being 1 means that 2 is not a factor of 6, 5, 7, 1. Is that okay so far? Then I try 3, and then some of you will say, but that's not smart. Well, maybe it's not smart, but is it wrong to try 3? Nope. So, with 3, we have 2, 1, 9, 0, with a remainder of 1. So once again, since the remainder is non-zero, 3 is not a factor of 6, 5, 7, 1. Next, I try this. 6. Question? 6, 5, 7, 1. And the next one, I try 4. And most of you say, well, that is just wrong to try 4. Well, is it really wrong to try 4? In other words, can it give me the wrong answer? Can it accidentally say that, oh, guess what? 4 is a prime factor of 6, 5, 7, 1. Is that possible? No, it's just dumb. Okay, this is just a waste of time. because if 6571 is not divisible by 2, it cannot be divisible by 4. But it won't give me a wrong result. It is just a waste of time. Okay, so I'll go ahead and do it anyway. So we have 1, 6, 4, 2, with a remainder of 3. I guess it is not. Okay, I guess 4 is not a prime factor of 6571. But I can keep doing this. Now, next one is division by 5. And most of you will say, yeah, but Tech, that is also dumb because it doesn't end with a 0 or a 5. Why do you even bother to divide it by 5? But when a number is represented as a binary number, you can't use that trick anymore. Okay? A lot of the tricks that we use to determine whether a number is divisible by a certain thing cannot be applied when the number is represented as a binary number. Yes, we can always convert a binary representation back to base 10 and then use the tricks that we know, but the conversion process itself is lengthy. Okay? It consumes a lot of time. It's not worth the time to go from base 2 to base 10 just so that we can use the limited rules of thumb that we know. Okay? So it is much better for us to derive a very general method that works all the time with all the different type of possible factors. In this case, if we have 1, 3, 1, 4 with a remainder of 1, and then I will try 6. 6, 5, 7, 1 divided by 6. Obviously, not a very smart move, but I cannot skip 6 or 4 or 8 or 9 or 10 unless I already know the prime numbers. Okay? At this point of this class, we have not talked about any mechanism to remember a list of prime numbers. And as a result, it is not possible for us to only try prime numbers. Are we okay so far? Does everybody understand why I'm trying all these composite numbers too? Because it is, one, it's the easiest thing to do, at least at this point. And two, if I want to optimize something, I have better ways to optimize it, which we'll talk about a little bit later. So this is not smart, but we'll try anyway. So 1, 6, this is a 0. This one is a 9. 3, 1, 6 with a remainder of 1. Okay, how about 7? I think you guys get the idea, what needs to be done here. 9, 3, 8 with a remainder of 4, 5, and so on and so forth. Okay, when do I stop? 13 I know is not a factor either, so I have to keep going, right? 13. The next one will be 8, because remember I cannot skip the non-prime numbers because I don't have a table of the prime numbers. I don't have a way to store a table of prime numbers. So 13 is not. How about 17? Is 17 a factor of this number? Well, the quickest way to do it is to go look for the answer. List of prime numbers. So let's see if this is a prime number itself. 6, 5, 6, 5, 7, 1 is not a prime number according to this. So it has a factor. Now, how far do you think I have to go before I find, if I know this is a composite number, what do you think is how much do I have to try, how far do I have to go before I find the prime factor of this number? It's about the square root of this number, right? Does it make sense that if this number is in fact a composite number, the factor has to be less than or equal to the square root of the number?